Good morning, ladies and gentlemen. My name is Sirawan Phiphiphatphaisit from Sirawan University, Thailand. The topic of presentation is the feature extraction technique based on Conv1D and LSTM network for food image recognition. I'll start to describe the introduction, then I'll mention literature review, contribution, and proposed approach. After that, I'll explain the experimental and experiments with deep learning method. Finally, I'll conclude our research. Overweight and obesity are the most significant factors for chronic disease. The easiest way to avoid chronic disease is to monitor and control people's dietary behavior. Advancements of artificial intelligence might help people to monitor and estimate daily calorie intake. Hence, food recognition systems are the most straightforward solution. The challenge of food datasets is that training sets contain some noise images, such as food images taken from different camera angles that make other objects such as people, tables, and bottles appear in image, as shown in the left figure, and similarity of shape, color, and decoration between two categories, as shown in the right figure. The researchers assume that computer vision can handle noise images and wrong label. Convolutional neural network has been extensively used in food image recognition research. Hassanajaz and others proposed a network composed of 54 layers with fine-tuned architecture for classifying food images. Leo and others invented the deep food network that modified the inception module by introducing one-by-one convolutional layer. In addition, Angular and others proposed the CNN fusion methodology. Martinez and others proposed Weiser network for classified food image. This table summarizes different food classification approaches. In this research, we focus on improving the accuracy performance of the food image recognition based on CNN architecture and LSTM network. We propose the deep learning framework that combines state-of-the-art ResNet 50, which is the convolutional neural network and long short-term memory network, called ResNet 50 and Conv1D LSTM network. This framework can extract robust features that are spatial and temporal features from the food images. Big data augmentation technique also involved while training the CNN model. In this experiment, LSTM and Conv1D LSTM network were proposed to create robust temporal features. For the Conv1D network, various layers were combined, including zero padding, back normalization, convolution 1D, rectified linear unit, back normalization, dropout, and average query layer. This section explains the framework for food image recognition. Two main architecture, CNN and LSTM network, are proposed to extract the robust spatial feature from the food images. Hence, the robust spatial and temporal features are extracted from the state-of-the-art ResNet architecture and the LSTM network. The temporal features extracted from the LSTM network are transformed into the probability distribution using a softmax function. For the spatial feature, we have proposed the effective CNN architecture to extract the robust spatial feature. In this study, we use 6 state-of-the-art CNN, VGG16, VGG19, ResNet 50, ResNet 201, MobileNet V1 and MobileNet V2. According to the computation power and time, the transfer learning approach is applied in the training scheme. Then the pre-trained model of CNN architecture are trained on the food image, and then examine the discover the best robust spatial features. As a result, the last pooling layer of CNN model is employed as a spatial feature. For temporal feature, we propose the Conv1D LSTM framework to extract temporal features from the spatial features. In the Conv1D block, the back normalization layer was added so as to normalize the input data and speed up the process of learning. The dropout layer was implemented to prevent overfitting. After that, the average pooling layer, which selected the average component from the subregions of the feature map, was considered as the feature vector. The feature vector was sent to the LSTM cell to learn and generate the temporal feature. Consequently, we again decreased the size of the feature using global average pooling layer before giving the feature to the submap function. In this research, we focuses on experimenting with the benchmark food image dataset, namely Food101 dataset. This dataset contains 101,000 real-world color images of 101 food categories. It consists of 75,750 training images and 25,250 test images. As explained in mentioned above, we first used pre-trained model of 16 in architecture to train and extract the spatial feature from food images. All scene and word trained using stochastic gradient descent optimizer, rectified linear unit for activation function, and learning rate between 0.01 to 0.0001 seconds. The spatial features were then sent to Conv1D LSTM and LSTM network to extract temporal features. In the LSTM network, the fractions of the unit was employed to drop the linear transformation of the input. The initial weights were randomly selected by using a Gaussian distribution where the mean is 0. This table presents the accuracy result on the test sets of the Food101 datasets for CNN, LSTM, and Conv1D LSTM networks. The results show that the Conv1D LSTM obtained the best performance with 89.82% accuracy when extracting features with LSTM 50. As a result, the Conv1D LSTM network by using average pooling and gap show better accuracy than other approach. We conclude that the LSTM 50 extracted the spatial feature with the high dimension and still provided higher accuracy when training with Conv1D LSTM and LSTM network. Hence, the LSTM 50 combined with the Conv1D LSTM, namely LSTM 50 and Conv1D LSTM, perform based on the Food101 dataset. To study the effect of the data augmentation technique, we apply 6 data augmentation technique: rotation, with shift, high shift, horizontal flip, shear, and zoom, while changing the scene and architecture. This table shows that LSTM and Conv1D LSTM perform better when applied data augmentation technique. As a result, the LSTM 50 and Conv1D LSTM network with the data augmentation technique provided an accuracy of 90.87% on the Food101 dataset. We made extensive comparison between our LSTM 50 and Conv1D LSTM network and existing set of real CNN architecture. The experimental results show that our network perform better than all CNN architecture. The accuracy of 90.87% was obtained from the LSTM 50 and Conv1D LSTM, while the performance of the wiser architecture was 90.27% accuracy. This study proposed the LSTM 50 and Conv1D LSTM network for accurate food image recognition. First, our network took advantage of extracting the robust spatial feature using LSTM 50 architecture. Second, we used the robust feature as input data for the Conv1D combined with the LSTM network, namely Conv1D LSTM. Finally, the submap function was employed to transform the outputs of the Conv1D LSTM into a probability distribution. The results show that the LSTM 50 and Conv1D LSTM network provide the best performance. Additionally, the data augmentation are impact to food image recognition. The result of the data augmentation also insignificantly increases accuracy by 0.27%. In future work, we will experiment on increasing the performance of food image recognition. We will consider other novel data augmentation techniques which could be more efficient in denoting food images. Also, the ensemble and parallel network will be involved in future work. Thank you for your attention.